In this video, we're going to review path and surface integrals for scalar and vector functions, and we are going to do that using this summary matrix. We will start with this chart of our path and surface integrals over scalar and vector fields. As you can see, I have divided it into a matrix. So over here on the first row are our path integrals. The second row are our surface integrals. And then in this column here, we're talking about our scalar functions. And in the rightmost column, we have our vector field functions. We will start in the first row, which concerns paths and line integrals. So the idea is that we have this curve and we parameterize it, or we make an equation for it based on a time t. So for every time t, we can calculate an x-coordinate and a y-coordinate. If we're in 3-space, we can also calculate a z-coordinate. Here, of course, I'm in 2-space. So for every time t between a and b, we can find an xy coordinate that we can then plot, and over as time progresses, we get this curve sigma of t. We can compare that to surface integrals, which is our second row over here. I have a video that talks about parameterized surfaces, but just a quick overview. So we can consider a surface as part of a plane, or you can think of it like a sheet of paper, and maybe the sheet of paper is cut into some special shape. It doesn't have to necessarily be rectangular. So it's a sheet or a part of a piece of paper, a plane. Often we talk about that as our domain D. And what we do with this, it's sitting down in the UV plane, so it's flat, and then we have this mapping which takes it into three-dimensional space, maybe twists it around, maybe stretches it some until we get our surface. And this mapping can be a very subdued mapping, or it could be a very exciting and dynamic kind of mapping, doing all kinds of pushing and pulling and twisting and folding. I like to think of this as a piece of pizza dough that you roll out on the counter, and then you throw it up into 3-space, and it takes some interesting shape as it's kind of tossed into the air. And that's the surface that's tossed into 3-space. So again, there's this function, which, because it looks like the green lantern, I sometimes call it the lantern function. The lantern function takes this domain in a plane, and it turns it into a surface in 3-space. So S is our surface, and it comes from a mapping, a lantern mapping on D. There are a couple of other things to know about surfaces, and that's in the u direction, you can take a fixed value of u and calculate a tangent line that goes on the surface over here, and you would calculate the tangent line for u with respect to u by taking dx du, dy du, and dz du. Similarly, you could take a tangent in the v direction. So holding v constant, you can find out what happens to that line and find the tangent to that vector. Then because we have two tangent vectors on our surface, we can calculate the normal by crossing the two tangent vectors. Last, if we have a surface defined as a graph on x and y, so in other words, here we have x and y, and then z gives us the points up here in the third dimension, then our lantern function is equal to xy, g of xy. So now we've talked about paths and curves versus surfaces, and now we want to do integrals over them. So the first type of integral we can do is a scalar function, and the second type is a vector field. So we should know the difference between the two. So for one, if I just look at this, scalar functions are denoted with a lowercase f, and vector fields are denoted with an uppercase f. So this might seem like a very picky thing, but it's extremely useful. So you would be wise to pay attention that when you have a scalar function, you have a lowercase f, and a vector field, you have an uppercase f. And a scalar function takes variables x, y, and z. Sometimes it's just x and y, but it takes a number of variables, x, y, and z, for example, and it maps it to a single number, a scalar number. That is a number without any magnitude or direction, it only has magnitude, no direction, so it's not a vector. So that's a scalar function. Takes multiple values, maps it to a single scalar value. A vector field, on the other hand, takes multiple values like x, y, and z, and then maps it into R3. So it maps it to an x, y, z coordinate. In other words, it maps it into a vector, which is why it's called a vector field. A quick example, just to make sure we have the difference between a scalar and a vector function. So here I have my scalar function written with the lowercase f. It takes an x, y, z, and it produces a number 2xy cubed plus 3yz plus 2. That's a 2 at the end. So if I plugged in numbers, 1 for x and -1 for y and z equals 0 into this equation, I would get a -2 for the first term. Because of the 0 and the z, I get a 0 for the second term and then a 2 for the last term. So I get a number 4. So this 4 has magnitude, no direction. It is not a vector. It's just a scalar. In contrast, if I have this vector field capital F, x, y, z is equal to 2xy cubed, comma, 3xz, comma, 2, when I plug in the number 1, -1, 0, I get the point -2, 0, and then 2. So this here is a vector with magnitude and direction. I had mentioned it was important, significant, this lowercase f for scalar functions and an uppercase f for vector fields. There's another important thing to notice, that when you have path or curve integrals, the ds is a lowercase. That tells you it's a line integral. This uppercase over here tells you that you're dealing with surface integrals. So you're also very wise to take note of the lowercase versus the uppercase s. In the path, it's lowercase. In the surface, it's uppercase. Now we are ready to talk about path integrals of scalar functions. So here we have the integral over this path of f, a scalar function, ds. And the lower cases mean this is a scalar function, this is a path integral. And here is the formula. I can break this formula down into 4 steps. So the first thing you want to do is parameterize your path, your sigma of t, and you're also going to write the range for your t going from a to b, whatever a and b might be. Second, you're going to write f in terms of sigma. That is, you're going to compose f with sigma of t. Third, you'll compute the derivative of your path. That will be your velocity. And then you will also compute the magnitude of your velocity. And then once you have all of these components, you're ready to plug into your integral. That is, you're going to have your limits of integration over here given by your limits on your path. You're going to have your function composition already computed. You'll have the magnitude of your derivative of your path computed. And then you're all ready to go. You can evaluate your integral. Also, you want to note when f of x, y, z is equal to 1, then your path integral gives you the length of your path. One other note, the reason why you do this function composition is because f, it's defined for all your points x, y, z in the x, y, z space. However, you're only integrating, or you're only concerned with the x, y, and z values that are on your sigma, which is why you plug the sigma values into f. Now we are ready to look at path integrals over vector fields. This is what the formula looks like. You have the integral over the path of capital F, that tells you it's a vector field, dot ds. And this is the dot product here. I tried to make the dots kind of a little bit darker. And this little ds tells us it's a path integral, just like this little ds tells us it's a path integral. Again, this formula tells us how to do our path integral, but I do have it written down in 4 steps, which actually are very similar. If you look at the scalar function, actually all 4 of these have the same essential 4 steps. So the first thing you want to do is find your parameterization of your path, including the limits for t going from A to B. The second thing you do is you compose your vector field f with sigma. In other words, write f in terms of your path. So f composed with sigma of t. And again, for the same reason as your scalar function, here your vector field is defined throughout all of 3 space for every x, y, and z, but you only want to integrate, you're only concerned with the x, y, z that are on this path, and that is why you do the function composition. The third step is you compute the derivative of your path, your velocity, and now you're ready to plug into your integral. The difference between these two, again, they're very similar, except here, instead of multiplying by the magnitude of the derivative, you do the dot product with just the derivative, because now you have a vector field. F of sigma of t, remember, is a vector, so you can dot it with the sigma prime of t, which is also a vector. Again, these steps are very similar if you compare them. There is a tangent form over here for this path integral, and the idea here is if you take your velocity and you divide by the magnitude of the velocity, you get the tangent, a unit tangent vector. So that's here. But if you divide by the magnitude of your velocity, you're going to have to multiply later by your velocity. And it's not so much that you're going to use this formula, because it's actually sort of a lot of work that you would divide to get the unit tangent, and then later you'd multiply by your magnitude again. But the important thing, and sometimes you'll have problems that this is very clear, the important thing is that this is telling you that when you do this path integral, it's essentially the components of f, your vector field, that is tangent to your path that gets summed up, that gets integrated. Another way of thinking about this tangent form is there's a physical interpretation of this vector field line integral, and that it is work done by your vector field f to move a particle along the path sigma. To look at this, I have drawn 3 situations. Here I have a path with the arrow indicating the direction of my path. So I have 3 versions of the same path. Here I have these arrows. The little arrows are a vector field, and I tried to draw as best I could this vector field being tangent to the direction of the path. In other words, it's going the same direction of the path at each point. And so the idea is that, and this is this idea here, that for this, the component of the vector field that helps move the particle on this path is a component that's tangent. And here, the vector field is totally aiding the movement of the particle along the path. Here I did another vector field. For the most part, it's going in the opposite direction as my tangent, as my curve. So in this case, and it's not exactly opposite the direction, but mostly is. So for the most part, this vector field hinders movement along the path in this direction. And then my last illustration, I tried to draw my vector field completely normal at a 90-degree angle to my fluid, my path motion, which means that it neither hinders nor helps. But this highlights that if you interpret this as work done by F to help move along the path, that when you're calculating this, you only want the component of F that moves with the path, that's tangent to the path. So again, the idea is this tangent form highlights the fact that we're interested in the component of F that's in the same direction as the tangent to the curve. There's one other form for this line integral of a vector field. If you write your vector field F as equal to a function for your x-coordinate, a function for your y-coordinate, and a function f3 for your z-coordinate. And then you consider your derivative of your path to be dx, dy, dz. So this is the derivative with respect to t of your x component, derivative with respect to t of your y component, derivative of t with respect to z. Then you can write this path integral in this form here, where you take f1 and you multiply it by dx, you take f2, multiply it by dy, and f3, and you multiply it by dz. And remember, f1, f2, and f3 are all, they end up being scalars once they're evaluated. We talked about surfaces. Again, they are these two-dimensional domains that gets tossed into the air in 3 space and then gets twisted and manipulated to make a surface. And we can take integrals over the surface, and we'll start with scalar integrals over the surface. So again, it's a scalar function, which is why we have this lowercase f. We have this uppercase s to denote that it's a surface integral. And here is the formula. And again, I broke down 4 steps kind of to associated with this formula, very similar to these other two. So you start off by finding the parameterization now of your surface. So it's our lantern function taking some space in the UV plane, and we're going to parameterize our domain, so the limits on the U axis and our limits on the V axis. Our second step is to write our function in terms of our mapping. Again, we're going to compose our scalar function with our lantern function. And for the same reason we did the function composition over here and over here, where is that? Over here, we're doing that here. And the reason is that this little f, the scalar function, operates over the whole 3-dimensional space, but we're not concerned about our scalar function f over here. We're only interested in it on our surface. So we only want the x, y, and z values that are on our surface. So we do the function composition. Next, we calculate a sort of derivative. We calculate our tu and our tv, which again are our tangent vectors. And then we calculate our norm, which is the magnitude of tu cross tv. And then last, we can plug all of our components into our integral. Similar to our scalar function, when f of x, y, z equals 1, then our surface integral is equal to the surface area of our surface. Last, now we have surface integrals of vector fields, so integrals of vector fields over surfaces here. We have our capital F to denote that we are a vector field. We have the capital S to denote that it's a surface integral. And here is the formula we use, but we break that down into 4 steps. The first one is to parameterize our surface, much like we did in this case. Then we compose f in terms of our lantern function equals f composed of our lantern function. And again, that's because our vector field is defined all over in 3 space. So f of x, y, z is defined at this point here, it's defined at this point here, it's defined at this point here, but we're only interested in the points on our surface because we're only integrating along the surface. So we only want the x, y, z values that satisfy our lantern function. So we do f composed of our lantern. Again, we calculate some sort of kind of derivative, and our derivative for surfaces is tu and tv, our tangent vectors, and then we calculate our norm. In this case, we're going to do the normal vector is equal to tu cross tv, but we are not going to take the magnitude. We just calculate the cross product, which gives us a vector. And now we can plug it into our integral, and because here we have f composed of our lantern function, this will give us a vector. Tu cross tv, the cross product of 2 vectors, gives us a vector, so we can dot the 2 together. Much like we did over here for this vector field integral, we dotted 2 vectors together. We also have our tangent form, much like we did over here, but this one we're going to actually use more. So our surface integral is equal to f dot n ds, where n is the normal to the surface, and we're going to use this especially when n is easy to figure out, not even calculate, just to you just kind of know. So easy surfaces, like something that's on a plane, is easy to figure the normal, or a sphere is easy to figure a normal, and we'll do problems with that. Surfaces are oriented, both of these. So there is a direction associated with those. Like you can see here, if you have a surface, your normal, you can have a normal pointing like up away from the surface, or you can have it pointing kind of down in the negative direction. So we consider the positive direction to be the outward direction. This one's harder to see, but if like you have a box, when you point into the box, that's negative. When you point out of the box, that's positive. These surface integrals of vector fields has a physical interpretation, which is called flux, which is the rate of flow across the surface. A negative flux means things are flowing into the surface, and a positive flux means things are flowing out. We have these theorems here, Green's theorem, Stokes theorem, and Gauss's theorem, which you may or may not have looked at yet, but I am going to go ahead and review them since they are really part of this chart. So Green's theorem gives you a way of relating a line integral around the boundary to a double integral of the curl over the domain. And again, the domain is a two-dimensional space, so it's a double integral, also emphasized by this dA, because the double integral is over an area. Stokes is actually a generalization of Green's, which we will discuss in a minute, but first we'll just look at Stokes on its own. So Stokes here relates the integral, a surface integral of a curl of a vector field, to the line integral around the boundary of the surface. And the boundary of the surface is defined as the lantern function of the boundary of the domain. So again, it relates a surface integral to a line integral, and it's the surface integral of the curl to the line integral of the vector f. So we can look at this again. We have a surface, and here we have a surface integral of the curl. So we take the curl and we look at the curl on the surface, and we can integrate over that. Or we can look at the line integral around the boundary. So that's this boundary here. And the way we get this boundary is we look at the boundary of our domain, and then we plug it into our mapping, and we get the boundary of our surface, which kind of makes sense. But it's nice because usually it's easy to parameterize your domain, and then you just plug it into your mapping to get the boundary of the surface. To see why I say Stokes theorem is a generalization of Green's theorem is because they both relate the line integral around a boundary, and in this case they're both these line integrals in the flat plane of domain D. In Green's theorem, it relates it to the interior, the integral over the interior of our boundary, or D, over all of D. Whereas in Stokes, it relates it to the curl over the entire surface. So again, it's still an area. It's actually D that's been kind of manipulated into the surface in 3 dimensions. One more thing about Stokes' theorem over here, when you take the curl of a vector field, the result of a curl is going to be another vector. So this whole thing here is essentially a surface integral of a vector. So the formulas and techniques to do this will be over here. This is a surface integral of a vector. And again, for Stokes' theorem, this vector field is the vector field that comes from taking the curl of an original vector field. So again, the curl of f produces a vector, so this is actually a surface integral of a vector, and the formula and the way to do it is located here. The last great theorem of vector calculus is Gauss's theorem, and it relates a triple integral over a volume to an integral over the boundary of that volume, and the boundary of the volume ends up being a surface. An example of what I mean is, let's say we want to do an integral over the entire sphere, and by entire sphere, I mean the interior all the way out to the surface. So Gauss's theorem will relate that triple integral for the volume to a surface integral, so just the very surface of the sphere, not the interior, and that'll be a surface integral as we've been doing over here. And actually we'd be in this box because it's a surface integral of a vector field. And one thing that I'm just going to point out is that the boundary of a volume is a surface. So you might have the volume of a sphere, but the boundary is just going to be the outside shell of the sphere. Or you might have the volume of a cube, like a die, and you might take a triple integral, which integrates the interior all the way to the exterior. Or you could have just the very 6 faces of the die. Those could be the surface. That would be the boundary of your volume. It's kind of what you would naturally think of as a boundary. And what Gauss says is that this surface integral here, which by the way, this surface integral is one of these. It's a surface integral of a vector field. So we're in this box of the matrix, is equal to the divergence of f over this triple integral volume. On this side here, this triple integral volume, it's like a plane, it's not one of these boxes. This is just a plain triple integral that we did a couple of chapters ago. And also I want to remind you, if you change coordinate systems like spherical, you need to use the Jacobian. Okay, so for one page, this is actually a lot of information. I hope you find it as useful as I do, and thank you for watching.